This is Chapter 13, Carbohydrate Metabolism, Commentary. In this chapter, we're going to go ahead and focus on catabolism and anabolism of carbohydrates, breaking down, for example, sugar into energy, or building up smaller molecules to form stored sugar or even bigger polysaccharides for longer term storage. So let's go ahead and begin. When you first eat, you need to go ahead and break down the larger di and polysaccharides into smaller monosaccharides. So these are hydrolysis reactions because we're using water to break them down, and as well as digestive enzymes in order to break them down into individual monosaccharides. The liver is the key controller. Too much glucose, the liver tells the body to go ahead and turn that excess glucose into longer stored glycogen. So it's not long-term storage like fat is, but it does allow the temporary storage of sugar molecules for later usage and being broken down for energy. If there's too little available glucose, then the liver tells the body to go ahead and break down that temporary stored polysaccharide glycogen into usable glucose, which can then be catabolized for energy. So the liver is the key controller. Now that we're in Chapter 13, and you will be given a cheat sheet for the final. All of this, Chapter 13 and 14, are going to be on the final. So in summary, even if I don't state it throughout, you need to go ahead and memorize. Basically, you need to know everything that's in the slides. Do I really expect you to memorize it? No. But essentially, it needs to be put on your cheat sheet. You will get a 8x11 double-sided cheat sheet for the final, which you can put anything on there. So you definitely need to have all of these items squared away on your cheat sheet. Glycolysis is when we go ahead and we start breaking down glucose into a intermediate molecule called pyruvate. This will then be used to create the molecule acetyl, which will then be used in your citric acid cycle. Basically, there's a lot of implied steps here. What I'm going to do is go ahead and try to step back a bit and give you the big picture. The first thing I'm going to go ahead and do is go back to Chapter 12 really quick. I'm going to go back to this slide right here in my attempt to give you a big picture of what's going on with glycolysis as well as upcoming steps. We're assuming that we've digested to individual sugar units, although there are many pathways which we just don't have time to talk about. We're going to focus on the most popular ones. And the most popular one deals with glucose. And glucose is going to be broken down into an intermediate molecule called pyruvate. Pyruvate looks something like this: CH3, C double bond O. This is also called pyruvic acid. So this is what pyruvate looks like. It's got a ketone and a carboxylic acid on the same biomolecule. From here, this intermediate molecule is then going to be broken down at a later step into the acetyl group, at which point acetyl will combine with the transport coenzyme CoA. So in this process of going from glucose to acetyl-CoA, you have a variety of, I'm going to go straight to the other one. You have a variety of steps required to get to this pyruvate. There's a total of 10 steps. This right here is an overall summary of what's happening. So notice you have a lot of support molecules, and some of the support molecules are meant to get the ball rolling, so to speak, to get the energy reaction going. And then other molecules are there to go ahead and pick up the excess energy generated. So in this overall summary, we start off with glucose and we start off with our NAD. As glucose is broken down step by step, it then goes ahead and recharges the NAD, putting on hydrogens and electrons, forming NADH. At the same time, it's going to go ahead and recharge our ADPs, providing energy to put on the phosphates, forming overall ATP. So here are the overall steps. Yes, everything you need to know. Again, this goes on your cheat sheet. Now, let's go ahead and go through these steps really quick. I'm going to first focus on the overall structures as the body starts reacting glucose in order to break down energy. And then I'm going to go ahead and focus on the enzymes. So here we have our starting glucose molecule. In order to get the ball rolling, so to speak, and here I have a potential energy diagram. Picture a boulder being right here. In order for me to get the boulder to start rolling, I have to go ahead and supply a little bit of energy and give it a bit of a push in order to, as I just said, get the ball rolling. Energetically, we're going to do the same thing. We're going to go ahead and we're going to start off using one of our already charged batteries, ATP, and we're going to go ahead and release energy. The phosphate that's given off in this exothermic reaction is then going to go ahead and replace that hydrogen, forming a new inorganic phosphoester linkage. The enzyme responsible for this is called hexokinase. Again, this is to go ahead and charge up our glucose to get the ball rolling, so to speak, so that way the subsequent reactions will start to release energy. But at this point, we're still adding in energy in order to get the ball rolling. So from glucose 6-phosphate, we're going to go ahead and rearrange and form a brand new isomer using this isomerase enzyme called phosphoglucoisomerase. Phospho referring to the phosphate, gluco referring to the glucose, isomerase referring to the fact that the sugar molecule is rearranging, forming a brand new fructose derivative, fructose 6-phosphate. From here, we're going to go ahead and donate one more ATP, giving off a phosphate as well as energy in order to really charging up this molecule. So it's at this point now you can think of it as the proverbial boulder that has enough energy to start naturally rolling down the hill. So from this point, what's going to happen is we have an enzyme called aldolase, and what it's going to do is it's going to go ahead and split apart the fructose 1,6 biphosphate. And it's going to go ahead and give you a sugar fragment here and a sugar fragment here. This particular molecule, dihydroxyacetone phosphate, is then going to be rearranged and form a brand new isomer due to this enzyme, phosphotriose isomerase. So they're both in the end going to be having this particular isomeric form right here. So with 2 glyceraldehyde 3-phosphates, it's at this point now the ball is starting to roll down the hill, and we can start recharging our NADs and ATPs. The ATPs are the ADPs, which are being recharged to ATPs. Yes, these can be used for future reactions, and they're ready to go. The recharged NADH is then going to go ahead and be sent or used in the electron transport chain for use in oxidative phosphorylation, and that process will then be able to create ATP from ADP, recharge ATP from ADP. So even though it's not directly creating recharging ATP from ADP, it does indirectly through this process right here. And we're going to go ahead and touch upon that again in a bit. For now, let's go ahead and continue. When this picks up hydrogens, it's going to go ahead and pick up the hydrogens as well as rearrange, and you're going to go ahead and create 1,3-biphosphoglycerate. The arrangement and the reaction that's taking place, the loss of hydrogens, is a little bit complicated, so I wouldn't sit there and spend a lot of time trying to figure out exactly at what part the atoms changed. Just make sure that you have this down on your cheat sheet. In this form, 1,3-biphosphoglycerate, using phosphoglycerol-kinase, it's going to go ahead and recharge 2 ADP to form 2 ATP. So keep in mind, from this part forward, we had 2 of these intermediate sugar derivatives, and so that's why we have 2 of our NAD being regenerated, and that's why we have 2 of our ADP being regenerated. In this form right here, it's going to go ahead and undergo, using an enzyme, phosphoglyceromutase, a change in the location of the phosphate ester linkage from carbon 3 to carbon 2, at which point, using the enzyme enolase, we're going to go ahead and lose a water molecule. And it's going to form a brand new alkene, at which point, using pyruvate kinase, we're going to go ahead and power up, or the recharge of 2 ADPs to 2 ATPs. This then leaves a still viable sugar intermediate, which we're going to be used to continue to break down in later metabolic steps. But this concludes the steps for glycolysis. Again, know all of this. Have it all on your cheat sheet. Now, it turns out that sometimes we have a lot of glucose, which we don't want to break down for energy because we don't need it. Other times we have very little glucose. So, we actually have a variety of modulators which help with regulating the breakdown of glucose. So, our first one is going to be feedback inhibition by a newly formed glucose 6-phosphate. And this basically is going to inhibit hexokinase. Now, keep in mind, our inhibitors and activators, they don't truly stop or truly start an enzyme. Rather, they slow it down or speed it up. So think of modulators as brakes and pedals. So if, let's say we have an excess amount of glucose, and therefore it's going to be inhibited. However, there's still a lot of glucose that could still form glucose 6-phosphate, and it will continue to undergo changes to fructose 6-phosphate. The enzymes aren't shown for this one. We just want you to show you the enzymes which are affected by modulators. So at fructose 6-phosphate, this is the last enzyme which can be used to inhibit any future glycolysis steps. So, it's inhibited by ATP and the biomolecule citrate, which is found in the Krebs cycle. It's also activated, or you can think of it as being sped up, by ADP and AMP. AMP is a basically an ATP that lost 2 phosphates instead of 1. So, phosphofructokinase can be inhibited or activated depending on whether you have a lot of ATP or whether you have very little, in which case it's in the form of ADP or AMP. So let's say we're low on energy, we don't have a lot of ATP, we have mostly ADP and AMP. Then it will go ahead and ramp up this enzyme to continue to push more forward. On the other hand, let's say we have all the energy we need, so we have a high amount of ATP, in which case it will drastically slow down this enzyme, slowing down the amount of production of fructose 1,6-phosphate. Once it gets to this point, however, it continues through the steps and doesn't stop until it reaches 3-phosphoenol pyruvate. Here is the last chance for it to slow down, although it could never completely stop, but just to slow it down. So pyruvate kinase can be inhibited by ATP. This slide summarizes what I've just said right here. Summarizes the key inhibitors and activators, as well as whether it's competitive or non-competitive. So glucose 6-phosphate is a competitive inhibitor of hexokinase, responsible for the feedback inhibition. Phosphofructokinase is a allosteric enzyme, and so at a allosteric site it's inhibited by ATP and citrate, as well as activated by ADP and AMP. Once it's converted to fructose 1,6-biphosphate, however, it must continue through glycolysis, at which point the brakes can then be applied at pyruvate kinase by being inhibited by ATP. So know this relationship, whether it's high or low. If ATP is high, then you have a high amount of an inhibitor. So it doubles as an inhibitor, which slows down glycolysis. If ATP is low, however, that automatically means ADP and AMP are high, in which case they act as activators to help speed up glycolysis. Now, again, it helps to have all of this in a big picture. So, I'm going to go back to the chapter 12 slides really quick. So, with glycolysis, we went from glucose to an intermediate molecule called pyruvate. From here, we're going to go from pyruvate to acetyl-CoA, which will then be later fed into the Krebs, aka citric acid cycle. Let's go ahead and give you another big picture, so to speak. Only this time I'm going to go ahead and focus on the location of where everything's happening. So in this case right here, and this is a great animation, by the way, which you can go ahead and follow the link in order to watch it. But here we have glucose, and it forms via glycolysis pyruvic acid. Notice it does give off ATP, and it regenerates ATP from ADP as well as regenerates NADH from NAD. It's not a lot, but every little helps. The pyruvic acid is then going to be converted into acetyl-CoA. Now, what happens is the pyruvic acid is converted to acetyl-CoA through two methods. And once it's converted to acetyl-CoA, then you could start to see what's happening. This brain-looking thing right here is a mitochondria, and the acetyl-CoA starts to get pumped into the Krebs cycle, aka citric acid cycle, and there are other steps involved. But at this point, I just want you to focus on this part right here, pyruvic acid to acetyl-CoA. There's two ways it will go ahead and form acetyl-CoA. The first way is let me go ahead and go back to my red pen. The first way is in aerobic conditions. This is when you have plenty of O2, oxygen gas. The second way is through anaerobic conditions. This is when you have very little O2. So this is when you are breathing hard, when you're undergoing intense exercise. The third way is actually not done by humans, although other select organisms such as yeast can do it. And this is where the organism will convert pyruvate into ethanol. So alcohol fermentation is most commonly done by the organism which we know of as yeast. So down below we see a general glycolysis summary. So this is just a recap that you first have to go from glucose to pyruvate, at which point we have these three options right here. So let's go in depth a little bit more into the first one. This is for aerobic conditions where we're getting plenty of oxygen. So here we have our pyruvate molecule, and with an available coenzyme and NAD, we're going to go ahead and use the enzyme pyruvate dehydrogenase complex to create acetyl-CoA. In the process, we'll go ahead and we'll regenerate our NAD to NADH, which will then later be used in the electron transport chain. The second way is under low oxygen conditions, anaerobic conditions. So this occurs when you're in deep exercise and you're trying to catch your breath. You're essentially not getting enough oxygen. So what the body does is it actually sacrifices its already available NADH along with pyruvate, and basically reduces it, turning a ketone into a alcohol. And this form we call lactate, also known as lactic acid. This is a temporary measure. It's not permanent and provides just a little amount of energy, although this is again a temporary setting. As we need to, as we eventually have lactic acid buildup, and we need to go ahead and actually recycle that into pyruvate at a later time, and we'll get into that a little bit later. But again, this is just a temporary measure to still allow us limited amounts of energy for the time being until we can get more oxygen. Here is a general equation. So this is the overall equation, which includes both glycolysis and the pyruvate reduction to lactate. So this overall process is referred to as lactate fermentation. So we're starting off with glucose, we do glycolysis, and then with not enough oxygen, we then go ahead and reduce the pyruvate into lactate, which provides limited amounts of energy, and again, it's only a short-term solution. We eventually will need higher amounts of oxygen to do our traditional aerobic respiration. This last one again is only for yeast. So although it's a very simple organism, it actually has a third option. And this shows the overall reaction, starting off with glycolysis and combining pyruvate reduction to ethanol, which we refer to as alcohol fermentation. So this converts glucose into a form called ethanol, and this is the drinking ethanol that we actually isolate and then add to our alcoholic beverages. So we can break, once glycolysis breaks up glucose into pyruvate, we can go ahead and we can show you the in-depth steps. So this is step 1, where we convert our pyruvate into a aldehyde called acetaldehyde using pyruvate decarboxylase. In this form, we then go ahead and combine it with an available NADH, where it donates its hydrogen, converting it into ethanol. Again, this is a third option, only done by specific organisms, not humans, such as yeast. So once we're in the form of acetyl-CoA, so assuming we're the organism is undergoing aerobic conditions where they have plenty of oxygen, we have acetyl-CoA, we're going to go ahead and transport the acetyl-CoA. I'm going to go ahead and open this up really quick. We're going to transport the acetyl-CoA into the mitochondria. So let me go ahead and go to this picture right here. So here's a pyruvic acid under aerobic conditions. It's been converted into acetyl-CoA, and it goes inside the mitochondria. From the mitochondria, the acetyl-CoA acts as the fuel in the cyclical pathway that we call the Krebs cycle. And there's a back-to-back set of biochemical reactions where eventually the very last product becomes the reactant, combining new acetyl-CoA, and again it's a cyclical process. Again, the acetyl-CoA, the acetyl group in the acetyl-CoA acts as the fuel, and in the Krebs cycle, its purpose is to go ahead and regenerate NADH from NAD. So we basically added electrons and hydrogens to NAD, forming NADH. We also do the same thing, even though it doesn't show it on here. We also do it with FAD, creating adding in pairs of electrons as well as hydrogens, forming FADH2. So that is the whole purpose of the Krebs cycle, is to go ahead and add hydrogens and pairs of electrons to NADH and FADH2. From here, it's then funneled into the electron transport chain, as well as another step called oxidative phosphorylation. And this is actually what gives us most of our ATP. So in this case, although we generate small amounts of ATP in glycolysis, the Krebs cycle, as you can tell, the majority of our ATP is generated using a combination of the Krebs cycle and the electron transport chain, along with the oxidative phosphorylation. So let's go ahead and go back to our slides. The acetyl-CoA again is funneled into the citric acid cycle, which all occurs within the matrix of the mitochondria. And the mitochondria is the powerhouse of the organelles within a cell. Here is the overall reaction. Again, the acetyl group and the acetyl-CoA acts as the fuel. The CoA is actually more of a shuttle, transporting the acetyl groups. And giving these starting reactants, it produces these overall products. Here is the step-by-step process. You have to be familiar with all of the steps. You have to, again on your cheat sheet, write down the name of the intermediate biomolecules in the pathway. You have to write down the individual side products as well as the enzyme names. And in a separate part, we'll show you the enzyme names. So to start us off with, it is a cyclical process because the final product is actually used as a reactant. The acetyl-CoA is a fuel, and the acetyl group is actually added on to the oxaloacetate, forming citrate. How they're added on, you don't really want to focus on that. Just know that it's added on. It actually adds on this portion right here. It's actually called an enolate reaction. Again, don't worry about the details, but it's this portion that's going to add on. The CoA shuttle leaves, leaving citrate. It then will rearrange, forming isocitrate, and then enzyme catalyzed form alpha-ketoglutarate. In the process, the carboxylic acids will form carbon dioxide waste, which will leave. At the same time, incoming NADs will then be protonated as well as have a pair of electrons donated to it, forming the covalent bond to NADH. There is another hydrogen that's given off, but that's just given to the solvent itself. In alpha-ketoglutarate form, we then have another NAD forming NADH. We have another carboxylic acid, which goes ahead and leaves, forming succinyl-CoA. In this form right here, we have a we can think of it as a different form of ATP. So it's a different type of battery, so to speak, that gets regenerated, called GDP, and it forms GTP. So this is actually used to power up other ADPs at later times. It then goes ahead and it forms succinate, at which point it donates two hydrogens, forming fumarate. So the hydrogens come from these carbons here, forming the brand new double bond, at which point water comes in and a brand new alcohol and hydrogen, a hydration reaction actually occurs at the double bond, at which point Again, another enzyme catalyzed reaction forms oxaloacetate, giving off 2 hydrogens, powering up the NADs. Again, the NADHs, the newly formed NADHs, as well as the FADH2, these are actually going to be sent to the electron transport chain, and between that and the oxidative phosphorylation, that actually creates the future ATPs. So these are important intermediate middleman biomolecules. And then the process repeats itself with a brand new piece of fuel, acetyl group that's added on, and then this cycle repeats itself. So make sure you know all these parts and you've added it to your cheat sheet. And this concludes part 1. In part 2, we'll get more into the enzymes and we'll get into regulation of this process.